So good afternoon. We are going to start our afternoon session today. So we are going to have two plenary talks. The first one will be presented by Dr. Zhonping Chen, and he is the director of the Functional OCT lab at the Beckman Laser Institute at UC Irvine. And Dr. Chen has a lot of experience and has been making a major contribution for the optical coherence technologies for different applications. Just after his talk, we are going to have the Dr. Teresa Bush, and I'll say the introduction later. So thanks so much for coming to Brazil, Dr. Chen, and have a nice talk.
Good afternoon, and thank you, Christina, and the conference chair to invite me to be here. And what a wonderful place to have a conference, and I really enjoy Rio. Today I'm going to just share some of the work we have done over the last few years on exciting technology on optical coherence elastography. And I do have a conflict of interesting disclosure with OCT medical imaging. So elastography is not new. Essentially, it's a technology to look at the mechanical property of tissue, and it essentially look at the strain and estimate the strain in the tissue, and a lot of disease actually involving change in the elastic property. For example, look at a liver tumor, look at ophthalmology, look at cornea disease, and so on. So currently, most technology using like MR and ultrasound. And so elastography can be work at many different scales, and they can look at, for example, from cellular structure using atomic force microscope, can look at a large organ such as liver. And traditionally, for example, most clinicians actually just using hands to look at stiffness of tissue and to try to diagnose disease. And the principle of the optical coherence elastography, or elastography in general, is really simple. So you have a tissue. If you have a different mechanical property embedded, you just apply a compression force and then just look at the displacement, and using imaging modality such as ultrasound, such as MRI. In our case, we're using optical coherence tomography. And later on, we will discuss why this is important for using optical coherence tomography and what's the advantage. And with the change in the displacement and the force you applied, we can calculate mechanical properties such as elastic constant. Now, obviously, you have to define a few quantity to quantify that elastic property. And there's two major constants. One is the Young's module, essentially representing when you apply a force, you have a compression, and if you look at the stress and strain, you can calculate that the Young's module. And the second is called shear module. Essentially, instead of apply vertical pressure, you look at horizontal force, and then you can see the displacement horizontally, and that force applied and displacement will give you the shear module. Now, in reality, both strain and stress are tensor quantity, so they are 9 by 9 matrix. And if you connect these two strain with stress, essentially you have an elastic constant, which essentially have 91 constant. And in our case, we want to simplify, at least for the first order approximation. So there's three assumptions. If we just assume that, first assumption is assume that the mechanic property within single voxel is uniform, so it depends how small voxel you define. The second is tissue is isotropic. I know many of you probably will raise your eyeballs, say, well, tissue is not isotropic. But for the first approximation, we just assume that tissue is isotropic. And the third one is essentially tissue is incompressible. And this is a reasonable assumption because 80% of tissue composition is water, and you can fairly safe to assume that water is incompressible within the force that we apply. So with that three assumptions, essentially the tissue mechanical property will become extremely simple. Essentially, you just have one quantity with Young's module, and the shear module and Young's module have a fairly simple relation that it's essentially 1/3 of the Young's module. So with that introduction, what I want to look at is why we want to do that, and what's the advantage of using optical coherence tomography to look at tissue mechanical property. Because traditionally, there is already a commercial system, for example, ultrasound and MRI, which essentially quantify the tissue mechanical property to look at the disease diagnosis in the pancreas, in the liver, in the thyroid, in the colon and prostate, and so on. But there's a lot of other applications that ultrasound and MR have not been very successful. For example, in look at ophthalmology disease, for example, cornea, and in look at cardiovascular disease such as atherosclerosis. And in this case, we need actually much higher spatial resolution compared to what MR and ultrasound can provide. So today I will just focus on one application to look at cardiovascular disease, and if time permits, I will also talk about corneal disease. So just give you some background and motivation why we want to do that, optical coherence elastography. We are really motivated by looking at a vulnerable plaque, and most of you know that the chronic heart disease is #1 killer in the Western, and in US, about 58 million have at least one form of chronic heart disease, and 50% of all cardiac arrest deaths are result from that disease. And one of the major fact is essentially is caused by a vulnerable plaque which rupture and cause either heart attack or if in the brain that cause stroke. And currently, if the plaque is stable, mostly they are fine. But what's really worrying is when they rupture. And so 80% of those plaque which ruptured is called thin cap fibroadenoma. And in order to capture that vulnerable plaque, we have to look at some of the property of that thin cap fibroadenoma, TCFA. There's three characteristics that imaging modality is required. The first is we need to have an extremely high resolution, so we have to be able to resolve thin cap less than 65 micron. The second is most of those vulnerable plaque has a lipid pore, so we want to be able to imaging that with fairly relative deep penetration depth. And lastly, we needed to have a molecular contrast or tissue mechanical property, because whether plaque rupture or not, or stable, really depends on the mechanical property of that tissue. So essentially, we want an imaging modality which can identify that thin cap. We want to know that how deep their lipid pore, and we want to know the composition of that plaque as well as the tissue mechanical property on the surface. So currently, intervention cardiology using two technology, and traditionally they're using called intravascular ultrasound. That technology has been there for almost 15 years. And last few years that optical coherence tomography get into the market. And these two technologies is really complementary. That OCT has much higher spatial resolution, but their penetration depth is fairly shallow, so they cannot see the full thickness of the plaque. And traditional ultrasound, they have very poor resolution. They cannot identify the thin cap, but they have fairly long imaging depth. So if we want to fully quantify that TCFA, and the best approach is probably combine these two technology. About 6 years ago, there's a study which motivates us to look at a way to solve that problem. And there's a study people actually essentially using OCT and ARF to look at patient with two imaging technologies separately, and then combine that histology analysis with that two imaging modality. And the conclusion is neither modality alone is sufficient to detect TCFA, and the combined use of OCT and ARF will be a better approach. So that motivates us to develop a system, essentially integrate ultrasound with the OCT in a single cathode device. So we can, with the single cathode, we have both the ARF transducer and OCT probe. And you can get essentially a co-registered image simultaneously with single cathode procedure. This is the cathode. It fits into the traditional ARF cathode. And you can see that this is the OCT image. This is from a human cadaver tissue. You can see that this is the plaque region, and this is, in this case, this is calcified plaque. And OCT can identify that the thickness of the cap very well because they have high resolution. On the other hand, the ARF can look at the depth of that thickness of that whole plaque. So you can combine these two images, which essentially solve the problem of high resolution and deep imaging depth. So we have moved this technology from the benchtop to in vivo study, and this is a look at the pig model, and you can see that again, you can see when they acquire image, you can see the plaque region. And so essentially, this is a pullback. So essentially, you get a three-dimensional construction of the whole plaque. So one of the question is, now we solve that morphology problem, can we get into the molecular contrast and also tissue mechanical property? So that led us to a number of wide search to look at the best imaging modality which can combine with OCT and ARF. So we have, over the last few years, we have done a look at the fluorescence combined with OCT, multiphoton endoscope combined with CARS, and look at the photoacoustic tomography, essentially look at lipid contrast. And today what I'm going to focus is look at the mechanical property using optical coherence elastography. So when we try to apply that technology to look at in vivo arthroscosis, one of the problems is traditional elastographic technique is limited because they have a relative low speed. We want a very high imaging speed. They have low sensitivity. And it's really difficult to implement into the cathode. So essentially, you want to have a device which can acquire high speed without apply a large force, and you want to be able to acquire the image at in vivo rate. So we look at elastography, as I mentioned, that essentially you apply the force, so you have an excitation method, and then you have a detection method. So excitation, you can have a static, just push it, for example, or you can have a jet of air compression, or you can just using a cardio cycle with blood pressure change, but those are relatively too slow. So what we decide is using dynamic excitation, what we call acoustic radiation force. Essentially just apply ultrasound force and push that at kilohertz or several hundred hertz. Then we want to be able to detect that displacement at extremely high resolution. We want to look at a nanometer or sub-micron resolution, because when you have a plaque, when you want to apply the force, you want to apply as minimal force as possible, because otherwise, if the plaque is unstable, then you apply the force, it becomes rupture. That's not good for a diagnostic technique. So we want to be able to imaging very small displacement induced by acoustic radiation force. So essentially, we're using a technique called phase-resolved OCT that we developed in the almost 18 years ago. And the phase-resolved technique was developed to imaging microvasculature. Our lab has been working on that for almost 20 years. So essentially, with that technology, look at the phase between the sequential scan or between the frame. You can image microvasculature all the way down to the capillary level. Okay. And what's the sensitivity of this technology? So if I just imaging a small displacement and look at the phase change with 1,000 average, the standard deviation give us a phase displacement resolution on the order of 40 picometer. So it's even small, less than a nanometer. So without the average, we definitely can imagine something that tissue displacement as small as a couple 100 nanometer or 10 nanometer and so on. So those high sensitivity have been adopted for many actually in vivo application. For example, currently there's a lot of study to look at microangiogram. This is one of imaging of one of my postdoc. You can see that we can mapping that vascular network very clearly down to the capillary level without applied any contrast agency. So essentially, this is just look at red blood cell flow in the small vessel. So with that technology, essentially what we measure is we measure the speed from the phase change, and with the time window, you essentially calculate the displacement, and from that, you can look at stress, and then if you know in the force, you can calculate the Young's module. If you know the Young's module, you can calculate the shear module. So here is the first experiments we're doing. Essentially, we have a swift source OCT, we have a spectral domain OCT, and then you have an ultrasound transducer here, and you apply amplitude modulated ultrasound, then using the OCT to look at their phase change. And the reason, so the ultrasound essentially itself is at 4 megahertz, but because tissue response cannot respond to that high excitation frequency, so essentially we'll modulate that ultrasound at about several hundred hertz to a few kilohertz. You can see that, so this is one of the phantom with a low concentration agarose, and here is the high concentration of agarose. You can see that when I apply ultrasound force, you can see that the tissue oscillate at the same frequency as my AM modulated ultrasound frequency. And for the soft tissue, you can see this is largest displacement. For the hard tissue, hard phantom, you see a small displacement. And when we compare the displacement, the ratio, they are proportional to the Young's module determined by the traditional compression test. Here is another phantom. You can see that portion of that phantom has a higher concentration, and the right side has a low concentration. Again, from the OCT image, you won't be able to tell the phantom difference. But because their mechanical property is different, when I apply the ultrasound force, you can see the left side oscillate much small compared to the right side. So from that oscillation and the amplitude, you can calculate the relative displacement. And again, this is the 3D rendering from OCT image and from OCE image. You can see that you can clearly see the boundary from the tissue mechanical property determination. Now, what happened when we look at the linearity of that excitation force? You can see there, this is the voltage applied to the ultrasound transducer, which is proportional to the force applied to the phantom. This is the displacement. You can see a very good linear relation. And when we compare to the Young's module test, the ratio, our displacement is 3.1, and the Young's module is about 1 to 3.2. You can see that they match very well. And here is imaging from a cadaver tissue from patient with atherosclerosis. And you can see this is a OCT image. This is the plaque region. And you can see that this is the OCE image. You can clearly see at the plaque region that the tissue is much hard compared to the surrounding tissue. So one of the questions is, it's great, we can imaging relative displacement, which essentially proportional to the tissue mechanical property. But in order to quantify that Young's module, you needed to know the force. And the force, if you have a planar geometry, probably you can calculate. But in a lot of cases in the vascular case, for example, the geometry is not planar, it's circular. Calculate the force is not that trivial. And so we want to looking for a technology which essentially will be calibration free. And if you look at a simple model, assume that the displacement, the force we applied is small, and you can see that there's a really simple relation between the resonant frequency and Young's module. So essentially, Young's module is proportional to the resonant frequency. In that formula, there is no force term at all. So we can essentially using scanning the acoustic radiation force frequency, and you can see that if I have two different type of phantom, you can see they have a two different resonant frequency. When I embed one from the other, in the OCT image, you cannot see that, but if I turn the resonant frequency to one of the objects that I try to visualize, you can see that object will get highlighted. So essentially, by turning the wavelength, you can look at the particular type of tissue that you want. And we also measure the resonant frequency as a function of the square root of Young's module. You can clearly see a linear relationship. And that so when we apply to cadaver tissue with atherosclerosis, you can see that here you have a fibrous tissue, okay, and they have a very loose structure, and here you have a dense fibrous tissue. And when I excite at 500 hertz at low frequency, that the loose portion of that will get highlighted because they are in resonance, and the dense portion has much small amplitude. But when I turn in the excitation wavelength frequency to high frequency, you can see that the dense portion will highlight. So essentially, you can turn in the excitation wavelength to look at particular property of the tissue that you are interested in. And so this is a very powerful technique to look at a different type of tissue biomechanical property. And we can also apply that to cornea. For example, in this case, this is in vitro study where portion of it we have using a cross-link, and other portion just the normal. You can clearly see the contrast between the two. And here is another diseased cornea. You can also see that using OCE, you can clearly see that. So the next question is, can we do that in an intravascular probe? And one of the questions we have is, can you excite that, still have enough excitation force when you have a probe down to a millimeter size? So we have not finished that study yet. We just construct one of the probe with 2.5 millimeter, which is still too large, but as a first step to test that. And you can see that we can clearly see that we can excite that tissue vibration with even a catheter-sized probe. So the second one I want to talk about is using shear wave and to look at tissue mechanical property. Now, essentially, you can excite that force at one end, and then that induced vibration will just induce a shear wave that propagates horizontally. And if we measure that shear wave propagation speed, we can calculate the Young's module. Essentially, Young's module equals 3 CS squared rho, and CS is the shear wave propagation speed. And there's many groups have done that shear wave, and but traditional shear wave, essentially you just excite at this location and just measure that the shear wave horizontally. And for some of the application that could pose a problem because the transducer and your imaging device occupy the same space, then you have a dead zone. So recently we developed a technology we called orthogonal excitation acoustic radiation force. So essentially we excite horizontally and imaging from vertical direction. And because OCT can look at not only a motion along this direction, but can also look at the motion along the horizontal direction, we can have a very high sensitive detection without worry about surface effect. So here's the experiments where we excite horizontally and look at from vertical direction. So this is the ultrasound excitation, this is the wartime image. You can see that for the left, you can see that there is a shear wave generated. It's a circle that propagates to the surface. And so this is a 0.5 agarose gel. This is 0.75 agarose gel. And you can see their propagation speed is different. Let me see, they will be coming back. And this one is much faster because they have a strong Young's module. And this is a phantom where I have two different types of material. Bottom is 0.5, bottom 7, at the top is 0.75. You can see that shear wave propagating into the interface. They actually will reflect, and portion of them will propagate. So from that arrangement, you can essentially see a pure shear wave propagation into the phantom, and where you can actually quantify that tissue mechanical property just by that shear wave. Here is again, you can see that they become not circular because it's interface. Now, I can look at phantom not only vertically, you can also look at horizontally and look at the shear wave. Essentially, you can, this is the left and right is different concentration. You can clearly see that from the slope, you can identify the tissue mechanical property. And we also applied it for the cornea, where you can look at shear wave propagation. From the shear wave propagation from the slope, you can quantify that tissue property. And we look at cornea with normal and with the cross-linked cornea. You can clearly see the difference in that shear wave propagation speed. This is 0.44, this is 0.46. And so you have a very powerful tool to measure that quantity. Another way you can measure that is just using M mode, essentially just stuck in one location, and you excite that ultrasound that measures that propagation of the shear wave from the bottom all the way to the surface. Again, you can clearly see that from that propagation speed, you can see that the shear wave can be measured directly. So this is a very powerful tool to look at different type of disease. Here you have a true phantom interface from that shear wave propagation from one side to the other side. You can see the slope change. Now, finally, I want to say that elastograph is a really relatively new technology, and over the last 10 years, they have see a very rapid increase in the research activity. I think hoping another 5 years that can be translated to the clinical practice. And finally, I want to thank you, the students and my collaborators. And most of the shear wave was done by Rachel and Dr. Zhu. And I have a cardiology collaborate, and ultrasound transducer is provided by USC group. Finally, I want to thank the funding agency that supports this research. Thank you.
So, okay, first question. Since we are running late, we have time for up to 2 questions.
Very nice talk. I was very interested about the catheter. How can you manage to do the radiation force? Because I imagine it has to be a very small element, right? And you have to rotate it, and in which frequency, and how is the speed of the rotation so you can have nice radiation force in the catheter?
You mean in the catheter, right? So essentially, it's a competition between your imaging speed and the vibration frequency you try to measure. And so that's why if you can excite really fast, so essentially you can filter out that the slow motion displacement.